is the current mirrors, and I'll kind of give you so today I'll just talk mostly why we need current mirrors, introduce you to the simple current mirrors, and then maybe, because next week I'm probably not there, maybe something you can take the wide swing, full cascode, maybe you can take that. But before I go, we'll just recap what we did for small signal modeling last class. And if you guys remember, the small signal modeling was for linearizing nonlinear circuits, right? So everything in the world is nonlinear. You know only linear tools. So you try to see if the circuit fall barely, or not barely, but if they are in the linear region, and you say, okay, they're approximately where I need it to be, and then you use your linear analysis to do that, right? So we took that inverter and made an amplifier out of it, right? So today I'm going to quickly show you another amplifier, which mostly you'll be using in analog design. See, the inverter, like I showed, we use it actually a lot in high-speed circuits, but typically we don't use that for low gain accuracy type of circuits, because in that you saw the biasing was not adjusted by any current source. It was basically whatever you got from the VGS, and the VGS was basically VDD by 2, right? Can we just switch on the fan here? It's actually, can you just switch on that AC, and we'll just put this fan mode? It's too cold for me. Yeah, can you give me that remote 1 second? Yeah, just put it in fan mode. Is it fan now or no? How do I stop this? It's like this place is either too cold or too hot. Okay, let's leave it here. All right, so like I said, that amplifier. So typically in analog design, especially when you're doing speeds which are way faster or way slower than what the technology can handle, then you typically are limited by power budget. So you'll be given like a 10 microamp current or 50 microamp of current, and you design with that. The inverter one, you don't have that luxury. Actually, you can. I haven't shown you how to do that, but maybe later on. But the way we analyzed it last class, we just sized it such a way that the input will just go to VDD by 2, where the VGS is VDD by 2. Then depending on the size, you're just going to get a current, right? So, and then the gain will be that GM times R naught, which was, 2ID over VF, 1 over ID lambda. So you get basically 2 over VF times lambda, right? So that's what you got, like the intrinsic gain. But typically you're given, so I'll show you a typical amplifier configuration. In fact, one of the most popular ones, which is called the common source amplifiers. And so you have one, let's say we do the NMOS one, you can do the same thing with PMOS. And the load as well as the bias current is biased by a current source. Okay, so this is basically your bias current, let's say IB. And this is obviously, I've shown it as the ideal current source. In the ideal current source, the output impedance is infinite. But let's assume that it has some output impedance, let's say some R naught, right? And then obviously you give a small signal to the gate, which is biased at some voltage, right? And this is biased at such a voltage that this IDS is equal to IB, right? And typically you don't do that in open loop. So it's not like somebody is sitting and adjusting that till it happens like that. It's part of a feedback loop, right? So if this is part of a feedback loop, that feedback loop will make sure, and that feedback loop is usually monitoring this output voltage. So let's say I want the output voltage to be 1 volt, then that feedback loop will keep adjusting the gate voltage till this is 1 volt, which means that this current will be equal to IB at that point, okay? So if I draw the small signal for this one, so what are the 3 steps? What anyone remembers what the 3 steps for drawing the small signal for this? So what are the 3 steps? What's the first step? What's that? DC bias, right? Find the DC bias because that's what you need to calculate all the small signal parameters. All your GM, RDS, they're based on DC bias. So like we said, this is linearizing a nonlinear circuit, but you have to tell where you're nonlinearizing it, right? Because if it was valid for all regions, then it's linear to begin with. You didn't need this. So you find the DC operating point, right? So this will be basically whatever ID, your IDS, VGS 0, and so on, right? Whatever you need, you basically do it. And then the second step is what? So, yeah, but before you do that, there's one more step. What do you do? Yeah, make the voltage source 0, but put it more generally, you make all independent sources 0, right? So you make all independent sources 0. So V is equals to zeros, I is equal to zeros, which means that this will be wherever you have independent voltage sources is short, and if it is a um, current source, it'll be open, right? So you do that, and then the last step is replace the nonlinear device with the small signal model, right? Small signal model, correct? So that's your 3-step method to do the small signal equivalent of any nonlinear circuit. So in this case, obviously we have one device which is nonlinear, which is the NMOS, and then we have just a current source as a load, right? So we first find out what VGS is, and then this will give you the operating point where it gives you IDS is equal to IB, and from this you calculate GM, RDS, GMBS, and all that, right? Once you calculate that, then you draw the small signal model, right? And like I said, initially when you're doing it, just replace it as it is, right? So that you're not getting confused. So you'll take this, and obviously here I'm assuming the bulk is shorted to the source. So if you take this, and then obviously from drain to source, you have um, the transconductance, right? Which is GM VGS and GM VGS. So let me say this is VI. And this is obviously shorted right now. VDD is shorted, which means this is ground, right? So, uh, so this is GM VI, right? Because VGS is VI. And oh, by the way, this is called common source because your the common point to both your input and output is the source terminal, right? Because the source is ground here. So your input is with reference to ground, which is with reference to source. Your output is with reference to ground, which is the source. So that's why it's called common source, right? So GM. So you have the transconductance, which is GMVI, right? So that's drain to source. So let's draw this as the source terminal. And the bulk and source are shorted here. So that is both, this is both your bulk and source, which is ground, right? Okay. And the input is given with respect to this node to VI. This is your gate terminal, which is just hanging because its input impedance is infinite because this is the low frequency model where the caps are not there. So if there was a cap, and we'll show you when when we do the high frequency modeling, we'll draw the cap. So there will be a CGS cap from this node to this node. There will be a CGD cap from across this, and there will be a CDB cap from drain bulk, which is drain to ground, and so on, right? That's your high frequency model. Because this model, you go to 0 hertz to 1 terahertz or 100 terahertz or terahertz, they're all the same. But obviously that's not true. After few, depending on your technology, after a few megahertz or gigahertz, this whole thing just will go, collapse basically, right? That's because the caps are not here. I mean, that's because the caps are there if it is collapsing. So this is a low frequency model. So your input is just a high input impedance. If you had the source here, this VI, so VI is basically connected between the ground and the source, right? And then we don't have the GMB, the transconductance for the source to bulk, because the source to bulk is shorted here. So the only thing we have is R, RDS, right? And a lot of times that is also called R naught, right? So RDS is also from drain to source. So you draw that. And then the last thing is the current source. So if the current source was the ideal current source, then that's it. That's your model, because your output impedance is infinite, because the current source is 0, right? So you basically open this, the DC part, you open it. So whatever impedance is left, that's the only thing which is across that current source. If it is ideal, there won't be any R naught. You don't have anything else. If it is not ideal, obviously nothing is ideal. So it has some output impedance. In this case, it's R naught. And that also happens from drain to VDD, but VDD is ground because we shorted that DC source as well, right? So this is R naught, right? And this is your V out. And, this is very simple. If you analyze this, you're going to get V naught over VI equals to minus GM times R naught parallel to RDS, right? And like I said, if R naught was infinite, then it would be just, if R naught was, very high, then it is just minus GM times RDS, right? And this is what's called self gain. So a lot of times if you are um, evaluating a technology, you see two things. You see how high a gain you can get, intrinsic gain you can get from a transistor, and what's the highest speed you can get. For the speed, and that's called the unity gain frequency, or FT. You must have heard what's the FT of this technology. You'll hear a lot that what's the FT of the technology. So we'll see how to get the FT of the technology from the high frequency model once you have the cap, because without the cap, obviously you don't have any frequency response. And that we'll probably see when when we'll start doing the frequency response of circuits. So far, I mean, till then, it'll be all low frequency analysis, okay? So this is sometimes called the self gain. And if you remember, GM was what, two times the bias current, which is in this case, we'll call it IB, because that's the current we are biasing it with, 2IB by V effective, which is VGS minus VT. There are two other equations also, which tells you what the GM is, which is 2 times ID times mu n C ox W over L root over. And then there's another one, which is, I think, what's that? 2 times V effective over root over of ID. It's basically just substituting the VGS minus VT with ID, and you get this various forms. So this is GM, and your RDS is 1 over lambda times ID, where here I'll call it same IB. Now, if you'll see some people use this as ID, some people will use it as ID sat, but they're very close. So when you do so this is VDS versus IDS curve for a given VGS, right? Equal to VGS 0. Now, if this is completely linear, you can predict the point here. So if RDS was equal to 1 over lambda ID sat, ID sat is the point where it just goes into saturation, then obviously you take the point here, it should be the same, it should be same here, because your R naught is nothing but this slope, right? That's your slope. But a lot of times you'll see, and it's not linear, because especially with short channels, it's not linear, but you can approximate that. So if you know ID sat, you can just say R naught is 1 over lambda ID sat. But a lot of times you'll see, if you don't know ID sat, you don't want to do it. And if it is not too far, your bias current, so let's say your ID sat is Your ID sat is this, but your bias point is here. That's your ID. Then you just use 1 over lambda ID, and that's pretty close. Okay. So here, that's what we're doing. And like as I said last time, lambda times the length, because lambda is actually inversely proportional to length. So lambda actually becomes smaller if your length is larger. And lambda smaller means your output impedance is higher. So a lambda smaller means this slope is getting more close to an ideal current source or an ideal transistor, right? The higher the slope, um, the ideal, it is close to the ideal device. The lower the slope, then it's not close to your ideal device, and it is inversely proportional to the length. So if you keep increasing the length, then this will, so this is a constant. Typically this is a constant, and like for example, in we said 0.18, it was what, about 0.08 or zero point 0.1, let's say, right? So that means this equation basically is 1 over V effective, and lambda is some K times L, basically, right? So that's your gain of this common source amplifier, approximately. So if you want to increase your gain, you lower your V effective, or in other words, you lower your VGS minus VT, and you increase your length. Okay, so that's the way. And the reason you do that is because GM is proportional to ID over V effective. So the smaller V effective you have, the higher the GM. That's the higher your transconductance. So means given voltage, higher the current, drain current, right? And similarly, um, RDS is proportional to 1 over lambda ID. So, and lambda is indirectly proportional to L. So if you want higher R, you want a longer length, right? It's directly proportional to length. So that's why. And when we do the FT for a transistor, you'll see that this is exactly the reverse. So for higher speed, you'll see you need higher V effective. Okay, so you need a big excess bias because you need more current. Okay, per gate capacitance. So this is kind of showing you current per gate capacitance, because you can just keep increasing W as much as you want, right, to get the current. But the problem is the person who is driving you, that thing is going to get slower and slower. It's like an inverter, right? You need an inverter chain to drive a really load cap, because if you put a huge inverter to drive a huge cap, then who's going to drive that gate? You'll say, oh, I'll put another huge inverter. Then who's driving that one, right? So it's the same deal here, right? You increase the W and increase the L, but then whoever is driving it will get slower, right? So that's why the self-gain FT kind of gives you an estimate on what kind of current you get for a given gate capacitance. Okay, so everyone clear here? Uh, any questions? People on the call, any questions so far? Okay, so no questions. Okay, so like I said, so simple 3-step for doing small signal. Like I said, when you're starting off, don't try to, I mean, if you can do it, good. Like try to make the circuit simpler in your head and draw it directly, right? Just replace it as it is. Draw the whole thing, replace the 3, and then short the VDDs, all the independent sources, voltage sources, open the current sources, and then simplify the drawing. That way it'll, you'll make less mistakes. And once you get experience, once you do it, you'll just look at the circuit and you say, okay, R naught RDS is parallel, GMVI is also parallel. You just write the equation GM times R naught parallel. But initially, when you're doing problems, make sure you actually draw the whole thing as it is in the circuit. And then as you short the independent sources, you make them ground and then simplify and make the small signal model. Okay. All right. Okay, I'll show you. Maybe what I'll do is I'll give you, um, I'll not derive the source follower. I'll give you that as exercise, but I'll show you how the circuit operates first. So source follower is actually used as a buffer. It's actually an impedance transformer. So instead of, I think I might have given you a problem uh, from in the same thing. You're applying a AC with some gate bias, VGS. Okay, and this is your VDD. This is your V out. So goal is find small signal gain V naught over Vi. Okay. So same three test steps, right? DC operating point, and the DC operating point here, it's actually given to you. You're forcing some I bias current to it, and that's and your VGS is whatever the VGS is. Once you find the DC operating point, short all the, I mean, make all independent sources 0. Here all that, how many independent sources here? 3, right? VGS, IB, and VDD. So 2 VDDs, VGS get shorted. So this will be a short. This will be a short to ground, so which is ground, and this will be a open. Again, you can assume some impedance R0, and then you can make it infinity and see what the effect is, right, later on. Okay, so so the source follower, as the name suggests, the output, it's a output follows the source. Okay, I mean, sorry, the source follows the input. Source is the output in this case. So source means source of this NMOS. You can do a same PMOS source follower as well. It'll be the reverse. So you'll have a current source, and this will be, I mean, if I have to show this accurately, you'll probably want to show it this way. Okay, so this is a PMOS source follower, right? Now, why does the source follow the input? From this circuit, who can tell me why is the source following the input? So source following input, in the sense, if I give a small signal change to the input, and the input is what? The gate terminal here, then the source follows it. Why does it follow it? And you can assume that the gate and source are shorted to begin with, and then you can make the problem where you're not shorting the gate and drain source. So why is the source following the input? Effective? ID and IB is same. Okay, what is the effective voltage? VGS minus VT. VI minus VT. Okay. But if the current is changing, then the voltage should change. So is the current changing? The ID is changing when I'm changing the input? Okay, but then the output should not follow the input, right? The VGS will change. Why is the current changing? Why is the IDS changing? Remember, this is the ideal current source. So let's say for this argument's sake, we'll remove this. This is an ideal current source, okay? Remember the ideal current source, what is it? No matter what the voltage across is, it's always IB, okay? Now, if you do a KCL here, right? There's only one node. I mean, there's only one other branch than IB, which is IDS, right? So if I have to satisfy KCL, the IDS has to be equal to IB. IB is never changing. So IDS should never change, right? Okay, someone from call, I think we're trying to answer. So why is the source following the gate?
Yes, sir. If M1
Sorry.
will be off, yes, sir. Vin is less than VTH.
Vin is less than VTH.
Yes, sir. Then
Okay,
M1 will be off, and V output will be 0. And in second condition, if V is greater than VTH, then M1 will be turned on in saturation region, and ID1 is followed through the RS. So that's why we're calling source follower.
No. You just said like three different conditions of operating conditions. There will never be cutoff, right? How will you cut off? So if you're cut off, why is the KCL, why is the KCL being violated? I mean, you have to publish this paper, right? You're violating KCL. If VI is less than VT and you're cut off and this is IB, where is IB going? Mhm. No, okay. So the first thing is, obviously, you should ask me which region of operation it is, right? That's not guaranteed because the VDS could be in linear region. So when you're designing these amplifiers or source follower, you want to make sure that this is in saturation. Okay, so that's the assumption to begin with, because the small signal we did was actually for the saturations, right? So that's the assumption to begin with. So if you're doing linear, then obviously then it's not going to be source follower. So the assumption it is in saturation region. So if it is in saturation region, why is the source following the input? So you bias it such a way that it is in saturation. Okay. So why is it following this? So the condition, like as I said, it is in saturation, right? Means you have IDS flowing. If the IDS flows and it is in saturation, so let's take an example. So let's take an example where this is 1.8 volts and this is 10 microamps and VT is zero point 0.4 volts, right? 0.4 volts and so on. So, and this is ideal current source and VDD is 1. So let's say I bias VGS equals to 0.9 volts. Obviously AC part is 0. So gate is 0.9 volts, zero point 0.9 volts. What will be the source voltage? It'll be 0.9 minus zero point 0.4 plus some V effective, whatever is the V effective. So it'll be a little smaller than 0.5 volts, right? This will be around 0.5 volts, right? So let's say it's just VT. For argument's sake, let's say it's just VT. So let me just clean this up a little bit. So I give 0.9, this is 0.5. Let's assume now the output impedance is infinite. There is no source bulk effect because the bulk and source is shorted, right? So, and V effective is really small. So the source is just VG minus VT. Okay, let's assume that. Okay, that's because whatever is the VDS, it'll adjust so that ID equals to mu on Cox minus VGS minus VT whole square should be equal to 10 microamps, right? And all I'm saying is that this VGS minus VT, this is close to, very small, close to 0. That's why it's going to fall. Okay, now I take this 0.9 to 1 volt. Okay, what will happen to the gate voltage? What will be the gate voltage? Again, source bulk is shorted. Let's assume RDS is infinite. Now, what was the condition for it to give 10 microamps? ID was equal to mu n C ox W over L VGS minus VT, right? Hmm? Yeah, so let me write this. So this is VG minus VS minus VT. VG was 0.9, VS was 0.5, and VT was 0.4, right? Correct? Now, when I change this to 1 volt, so VG goes to 1 volt, right? But this current still has to be 10 microamps. This is not changing. Mu n C ox W by L is same. VT is obviously not changing. VG is 1. That means what should be VS so that this quantity is exactly the same? 0.6, right? So this has to be 0.6 because 1 minus 0.6 minus zero point 0.4 will be close to 0. Obviously, you need the V effective is to be close to 0. That means this will go to 0.6. Now what happens if I take this to 1.1? It'll go to 0.7, right? So every 100 millivolts I change the gate, the source also goes up by 100 millivolts. Obviously, if I bring it down by 100 millivolts, it'll also go down by 100, as long as it's in saturation with all the assumptions we did, right? So that's why it's called source follower, because the source follows the gate. And this is small signal, right? Because the absolute voltages are different, because that's the DC bias. But small signal, if I get a delta V of 10 millivolts, the source also will move by 10 millivolts. So that's why it's called a source follower. So we use this to buffer circuits. So if your impedance is not matching, you did a amplifier, but you're driving a huge load, then you buffer it by a circuit like this, because what it will do is your input impedance looking in over here looks like just like a cap, but the impedance looking here, you'll see when you do the small signal analysis, it'll look 1 over gm. And if you bias this with sufficient high current, then that impedance can be lower. So for example, you want to drive a 8 ohm speaker from your cell phone. Have you ever tried that? Well, you'll get nothing. It'll be just like a headphone. So you can take that 8 ohm speaker and put it by your ear, because that's the power it can deliver, right? So your headphone usually requires about 200 milliwatts of power and just 32 ohms. So it just delivers 32 milliohms power because it just has that much current juice in it to deliver. You want to put a 8 ohms, you have the voltage, but doesn't have current to supply. So then you put a buffer like this. Okay. Then if it has the voltage to supply to 8 ohms, so let's say your headphone was 800 ohms, right? So you have 10x voltage to supply, but 8 ohms needs 10x more current too for that same voltage. So you have the voltage to provide to the gate, but you don't, I mean, to the speaker, but it just can't provide that much current. So you put a circuit like this, then it'll provide the current. So the voltage is provided by the amplifier, the current is provided by the buffer, right? So when we do op amps, you'll see that the first stage is a differential stage, which is like the common source amplifier. But then you have to, if you want to drive resistive loads, then you have to follow up with a stage like this to provide the current. So one imitates the voltage, I mean, amplifies the voltage. The output stage makes sure that you can provide the current to the load. Okay, so that's why it's called a buffer. So maybe the small signal model, I'll give it as exercise to you guys. Okay, same thing, like I just said. Now you have the DC, you um, and here assume that the source is not connected to the bulk first, so you'll have GMBS also. So derive the entire thing and take some output impedance of this guy, which is R0, derive anything, and see if that small signal gain is coming close to 1, like as you predicted from your DC analysis. Okay, if it is not, something is wrong, go back and derive it. And same procedure, right? Take the 4-terminal device, the transistor, plug the small signal model into it, solve, use your network equation, your linear network equation, the 3-step we follow. Choose your ground, choose your nodes. If it is a independent, there should not be any independent source. Well, there will be independent source in small signal as well, which is VI, right? Or I, whatever it is. And then write the KCL equations and solve it, right? So same thing as you did for DC, you do for the AC signal also, and then find out V naught over VI, and that should basically, if it is a source follower, that means V out over VI should be 1. Ideally, it should be 1, but because you're going to take the bulk effect into picture and the R naught into picture, you'll see that there is an error. And then you make the R naught infinite, GMB equals to 0, it should be exactly equals to 1. Okay, and that will tell you what is the effect of GMB and so on. Okay, so maybe do this as an exercise. It's a good exercise to do. All right, so now I'll talk a little bit about why current mirrors. Yeah, how is the current increasing? Current is not increasing, right? I said it remains the same. Oh, I see. Okay, good question. So basically what Subham is asking is, why is the current increasing? It actually is not increasing. So what you do is you have IB, right? So like as I said, you have your big fat speaker here, right? Something like that. And this looks like a 8 ohm resistance actually, right? 8 ohms. So it's not like the current is increasing here. So what happens is when you increase the voltage over here, whatever current is needed by this guy will be provided from this guy here plus IB. Okay, so let's say this is 1 volt and it requires 100 milliamp, something, I mean, it's 8 ohms, so it should be 8 amps. But so let's say, what did I say? I mean, change this. So, so let's say 800 millivolts divided by 8, so that'll be 800 milliamps. So, right, so you need 800 milliamp, right, over here. So obviously, if you bias it with 10 microamp, it's not going to cut it, right? So you need to bias this at least with like 1 amp. And that's why all the big power amplifiers will have huge current. In IC, you don't bias it this high a current, but outside you'll bias it this higher current, right? So when the signal is swinging, this is always 1 amp, right? So let's say you need 800 milliamp here. What should be the source current here? 1.8 amps, right? When this is 500, this will source 1.5. And when it has to go to reverse, so let's say the current needs to flow 500 milliamps in this side, this way, then this only needs to supply 500 because it's 500 plus 500 is 1 amp. Okay, so this is what's called a class A amplifier. Okay, sorry. So this is, ah, this is called a class A amplifier. Okay, so you can see if I want 1 amp, this is really not a good idea because you're, no matter how much current you're providing to the speaker, you're always drawing 1 amp times VDD. Not a good idea, right? Because that's a huge power loss. So typically in big power amps, you want efficiency close to 900% basically. So efficiency close to 100% means you want this current to be basically zero. You don't want to draw any current here. And that's why you'll see in real power amplifiers, they don't use class A. They will use something called class D or class AB. So which actually provides only the current needed to the speaker. Okay. But then you get into distortion issues and all that. So there's like 100 or 300 years of research in that field. It's just like one of the oldest areas people are working on. But for really small amplifiers where you have small currents, you just bias it class A because you try to do class AB for very small, then you end up actually burning more current, your circuit being more complex, your circuit being more area, and so on. So typically when we are doing 100 microamps, 10 microamps type of amplifiers, they're just class A's, even half a milliamp, depending on your application. If you can't tolerate that kind of power loss, then obviously you have to think about other ideas. Okay. So that's what's called the bias current for a class A amplifier. Okay, so why current meters? So I'll quickly try to show you how we bias discrete circuit. Before we started doing IC design, how did we bias circuits, right? You guys have like kind of gotten out of that. People, used to do discrete a lot. Now people just put ICs. They don't do discrete, right? So so let's take the amplifier we just talked about, right? A common source amplifier. Let's say we want to do it in BJT because, older days there were no MOS external, so it was BJT, right? So if I do the same amplifier in BJT world, it'll be something like this. Okay, so that's your VI and that's your V out, right? This is VDD. This is common emitter, exactly. So instead of a common source, this is a common emitter, right? Amplifier. That's because the emitter is common to both output and input. Okay. And same principle here. So let's say this is RL, small signal gain. GM is ID over VT for a BJT, right? And VT is just the thermal voltage, so it's GM times RL is your gain, right? So which is ID times RL over VT. That's your gain. Okay, so you figure out a gain and all that. So let's say, take some values. This is 10K and you want to bias it with some current ID. So let's say this is 5 volts. You want this 2.5 volts. So your ID should be what? Um, 250 microamps, right? So this should be 250 microamps because 250 microamps times 10 is 2.5 volts. So that'll make sure that this is sitting at 2.5 volts, right? Now, how do I force to 250 microamps here? I mean, you can apply a gate voltage, kind of tweak it ever so slowly. When it's exactly to 250 microamp, you stop, right? But then the temperature goes up a little bit, then it's gone, right? That output is just railed. Then somebody comes in and tweaks it, and then it's gone, right? So that's not a good way to bias it, right? So um, so typically in deep circuits, the way you bias it is you actually what you called is you degenerate the emitter, okay? And then if you put this voltage, so let's say this voltage was zero point 0.5 volt, and let's take some examples. So this is, let's say, 1K. I want to put 250 microamps here. That means this voltage needs to be at what voltage? 250 millivolts, 0.25 volts, right? So 0.25 volts here, and this is 0.5. I mean, the 0.5 is the VBE, so you need to bias this gate voltage at 0.75, right? 0.75. So I can just put a resistor divider between VDD and um, the base voltage such that this is 0.75 volts. So let's say this was 5 volt, then you calculate R1, R2. Let's say this was R1, R2, you calculate that and do it. Okay. And then in order to couple the AC signal in, you actually bypass this because you don't want to take this DC voltage and affect whatever it is driving. Like the cell phone example I was giving you, your cell phone has some DC bias into it. If you directly attach to it, you'll draw a huge current and you'll just collapse it, right? So you want to just decouple it, but AC couple it for bigger signals, okay? And then what you do is you actually put a cap here too, and your output is this. Why do you put this cap? This is usually called CE. Why do you think I need that cap? Hmm? If I don't put this cap, what happens? It's actually almost close to a source follower, like I decided before, because this resistor looks like almost like a current source if it's a high value resistor. So this node will follow the source. If this node follows, then this current will be this divided by this current times the RL resistor will give you gain. So instead of GM times R, it will be actually, so let's call this RE, your gain will be actually RL over RE. And a lot of times we will use it to do it that way. But if you want to actually make really high gain, then you want actually GM times RL because that's where you get the maximum buck for your current flowing through it. So then you do this so that for AC, this looks like a short. You look like a common source amplifier. But for DC, it looks like a common emitter so that you just DC bias it properly. But for AC, you do it this way. Okay. So typically, this is how you would have biased it. If you're doing discrete designs like older days, or even now, you did it, you would bias it this way. Okay. But in IC, we just can't afford to do it this way. Okay. So can you tell me what are the problems you think biasing it this way? So instead of a BJT, I put a MOS and start biasing it. What will be the problem? Biasing it. Resistance. Okay, what's the problem with resistance? Large area, good. Yeah, that's one problem. Exactly. Um, you can choose resistor values to be much larger compared to, and that's where the large resistor comes into picture. You want, like for example, you want this current to be as low as possible. That means the resistor needs to be really huge, right? So in discrete design, a 1K resistor, a 1 meg resistor, a 100 meg resistor, a 10 ohm resistor, a 0 ohm resistor, they're all same, right? If your power rating is, let's say, quarter watt, there'll be a 0805, like those small tiny resistors, right? So they're all the same size, same value and everything. But in IC design, they linearly are proportional to your resistor value. And then if you increase your W, they increase even further, right? So that's the main reason why you don't do it. And same thing about the capacitors too, right? So these capacitors, if you use them for low frequency, they're huge, right? They're in nanofarads or picofarads. And you're talking about like in 0.18, I think it's roughly about 8 femtofarad per micrometer square. That's gate cap. That's like the highest cap density is the gate cap. If you go MIM, that's 1 femto. And if you go like finger caps, it's even lower. It's like 0.025 or 0.25 femtofarad per capacitor. So when you're trying to realize the picofarad, the size is just huge. Okay. So that's the reason you don't do this. Um, so in IC design, that's why you're usually given a power budget. And because of that power budget, each of the circuits, you'll be given how much current you're going to draw. And you basically just bias those circuits by those currents, okay? Now, this is where current mirror comes into picture, because in order to create a current source, so typically a current source is created through a band gap reference, okay? Or it could be just a simple circuit as a VT over R, okay? But this is a big, huge circuit, okay? So let's say a band gap circuit could be as big as like 200 micron by 100 micron, okay? But it gives you a nice current source, okay? If you design it well, it'll give you a nice current source. But I need now thousands of those things copied, right? So let's say this was my BGR and it gave me a nice like 10 microamp source, right? Now I have like this circuit one requiring, let's say, same 10 microamp. I have another circuit requiring 20 and so on, right? If I create a BGR for each one of them, then the size of your chip will be the size of this table, right? I mean, it'll be huge. Instead of 1 millimeter square, it'll be like 1 meter square. So it'll be huge. So that's where current mirror comes into picture, is that you take one pristine source, okay? This is your 10, and you basically mirror them, okay? You create mirrors, you do whatever magic you want to do, and that's the magic we'll do uh, in next slide. And you basically ship all these currents. So obviously, if you need 20, you either take two of them and put it in parallel. I mean, that's what you essentially do, which is doubling the size, and we'll come to that. And then obviously you just keep, you know, doing that, right? So that's how we bias in ICs, right? And okay, and that's really the motivation behind current mirrors, because it's just very efficient to bias circuits in analog circuits. Um, Clear? Okay. All right. So, okay. Actually, before I move, people on call, any questions? We're on call. Okay. I'll assume that no. All right. So current mirror, as I said, it uses as bias, but it's also used as the load, right? So because um, okay, let me see how. All right, so let me take this example. So we took an example just before where we said we put a current source to the drain of a common source amplifier, and that gave you the gain, right? You could do it like the BJT example I showed you, right? So you could do it this way. You have a common source and you have a resistor here, right? Some RL. And then obviously you bias this, some bias voltage, that's your V in, this is your V out, right? So you could also do it this way, right? And if you do it this way, what's your, so let's see now if you can start doing the calculation in the head. So what's the gain for this? And I'll give you maybe a condition where I'll say RL is much, much less than RDS, let's say. What's the gain for this amplifier? Hmm? Yeah. From now on, when I'm saying amplifier source followers, we're assuming it's in saturation. That's like, you just take it for granted. Okay. Because there is no point having a transistor in cutoff trying to do amplifier or in linear region, right? Minus GM, yeah, into RL, right? Because you see, last time you had R naught here, which was the output impedance of the current source. It came in parallel with RDS. So RDS parallel with RL, but I said RL is much larger than RDS, right? And so minus GM. And what's GM? What's the 2 times ID? 2 ID over V effective times RL, right? Now this ID RL, this is actually the voltage which is dropped from here to here. right? So that's one of the biggest problem, right? Why is it a problem? Maybe I should ask you, what's the problem? Anyone on the call, what's the problem? I mean, you can design it. There is no, I mean, when I say problem, it's not like you cannot design it at all. You can design it, but two things are coupled, right? So why is that problem? So my small signal gain is coupled. This voltage drop is coupled, right? So why is that a problem? Okay, let's take an example, right? So let's say the VDD was 2 volt. This is 1K, or 1K will be too little again. This will be too little again. So let's say 100K, 100K, and so I want this output. Ideally, where do you want that DC output to sit? Because when I give a signal, it should go up and down. It's a AC signal, right? If I give a sine wave from that point, so if I give a small signal sine wave, this should do a large signal sine wave like this, right? So if I want the amplifier not to clip, right, for a certain input of voltage, where do I ideally want to sit? 1 volt, right? Because that way it'll allow me to go 500 millivolts up, 500 millivolts down, assuming everything remains in saturation still. Um, and if I bias it at 0.575 volt, then if I go 250 millivolts, then it's clipped. I have 750 millivolts down headroom, but I have only 250, so it's useless, right? So typically you want to bias it in middle, right? Now, if I want to bias that at the middle, and so that's 1 volt, right? And this is 100K. Let's say I need 100K because GM times RL turns out to be 100K. Okay. But then they're not decoupled in the sense that if you give me ID and you give me V, okay, then, so let's say I'm given a power budget. So somebody gives me a power budget and says, whatever you do, your current should be 100 microamps here. Okay. And this is 1 volt here, right? If that's 1 volt, then I don't have anything to do with RL. The RL has to be what? This is 1 volt and this is 100 microamp. 0.1 milliamp. 0.1 milliamp for 1 volt is how many? What is the voltage you need? Or let's say I make it 1 milliamp, just to make your life easier. So what should be RL? 1K, right? This should be 1K. So this is fixed. Now I have to go and make this V effective as big as small as possible to get my whatever gain I want. Let's say I want a gain of 10. This is my only thing which is left with me to play around with it, right? So the DC and the AC gain are not decoupled. They're actually coupled. In our previous example, the R naught was to do with length, right? And ID, but the IDs were canceling because the GM was proportional to ID. RDS was inversely proportional to ID, so they canceled, right? So it was only proportional to L. So I can bias the output at any voltage, and bias current, I can bias it to any bias current independent of it. So that's desirable, right? Because then it allows me to, pump more current, work with a smaller device, or pump very little current, work with a larger device if it is a slower amplifier. Whereas here, if I'm given a current, I'm stuck with it because I need 1 volt at the output, right? So that's why the gain and the DC function, they are coupled with this IDRL. So that's why it's not desirable. Plus, like I said, having a um, um, resistor is too big a area. So that's why we use a current source. So the current source allows you to bias it as well. It serves as the load also for this to give you that high gain, right? Because now the gain is GM times, this gain will be GM times RDS parallel to the R naught, which is R naught is the output impedance of the current source. Okay. But your DC voltage there can be anything as long as the current source is in saturation and the transistor in saturation, right? So it'll be working fine there. So that's why the current mirrors provide both as an active load as well as the bias current for it, and they kind of decouple your small signal gain from the DC bias as well. So that's another desirable feature of having a current mirror bias your amplifiers. Okay. Okay. How do we create current mirrors? So let's say uh, I give you a 10 microamp source from VDD. So this is your N. How would you create a current source? I mean current mirror, knowing everything you know till now. So let's say you're going to use NMOSes, you know how to bias your NMOSes, you know the current equations and everything. How would you create this current mirror? Okay, let's take a transistor, some size, I don't know, like 10 by 1 micron or whatever it is for 0.18. Okay. And so if you look, what is the current equation for this? In saturation, let's assume it's saturation. Mu n Cox O2 W over L VGS minus VT square, right? Okay. And I want this to be 10 microamps, right? So VT is known, W over L is known, obviously mu n Cox is your technology parameter. So the only thing which is not known is VGS. So you calculate VGS, right? So VGS is equal to, what is it, 10 microamp over this quantity here, root of that plus VT, right? That's your VGS. So basically this quantity is your V effective or V on or VD sat, all those names you have. So VD sat plus VT is what you need, right? So let's take an example. So let's say VT is equal to 0.4 volts and VD sat or V effective or V on is equal to 100 millivolts, so 0.1 volts. So what is the VGS I need to 0.5, right? So I just need to put 0.5 volts here, and the VDS needs to be what? Greater than VGS minus VT, right? You want to be in this region, right? That's your current source. Obviously not a ideal current source because the current is varying slowly, but it's your ideal. So as long as this is greater than VGS minus VT, I almost have that I need, the 10 microamp current. It's going to vary ever so slightly, but your output impedance, if it is higher, and that's what we're going to talk about. So, when Santanu is going to talk about the cascodes and wide swing mirror, that's how we'll see how to take this curve and start making it flatter and flatter and flatter and so on. Okay. So that's it. Okay. How do I create this voltage? So I have this current. I want this voltage. How do I create it? Resistor. Okay. Let's do that. So let's put a R here. I'll pump this current in. It'll generate a voltage and you create this, right? It's easy to calculate, right? What will be this resistor value? 0.5 over 10 microamps, right? Which is what? 500 millivolts, 10, 50, 50K, right? Is that right? Roughly 50K. So I put a 50K resistor, it provides the current, and I can keep doing this. And so this is what I ship it out now to circuit 1. And I can keep doing this. Just take this gate voltage and take it to circuit 2. Circuit 3. Okay. As long as this circuit makes sure that this voltage is greater than VGS minus VT. So like for example, here we took 100 millivolts. So as long this is greater than 100 millivolts, these guys will get a nice 10 microamp current or a pretty good 10 microamp current, right? Okay. So, but the problem with this is in theory, this is fine, right? There's no problem with this in theory. What you have said is it works perfectly fine. But in practice, uh, if you're trying to get any kind of accuracy, this will just kill you for a couple of reasons. One is as the temperature varies, the way the resistor varies, the VGS varies, the VTS varies, they're completely different. And you remember, this is a square term here, right? Any gate voltage varying here will make the current vary quite a lot, right? Same thing, the resistors in ICs, they're plus minus 20%. In other words, you took the row, you decided what should be the W over L, you created a nice 20K resistor, I mean a 50K resistor, you plugged it in, you get one part, it's 40K, you get another part, it's 45K, you get another part, it's 55K, you get another part, it's 60K. It'll just vary, right? It can vary all over the place from process to process. Temperature you do from minus 40 to 85, your consumer, that itself will make it vary by almost 5%, right? So that variation is huge. Plus, when I'm doing this small current, you can see that's a huge resistor as well. And if it is one resistor, it's fine. But the biggest problem is that it will not match. So both for mismatches as well as process and temperature variation, the current will vary quite a lot. Okay, so that's the reason we don't generate the voltage this way. So we'll not generate the voltage this way. Okay, now tell me, how can you generate the voltage to remove this variation now? So this is 10 by 1 micron device, right? Right. Now, if I take a 10 micron device and force a 10 microamp current into it, I mean a 10 by 1 micron and force a current to it, what would be the VGS? So if I do this, and what I'm going to do is I'm going to monitor this voltage and make sure that this drain current is 10 microamp, and I'll put, so let's say I have a voltage source, right? I have a voltage source I'm varying. If this voltage is less than 0.5, what will happen? If this voltage VGS is less than zero point 0.5, what will happen? See, I need 0.5 exactly so that this is 10 microamp, right? If it is less than zero point 0.5, what will happen? That's the ideal current source. It's saying, I am not going to budge from 10 microamp. It doesn't matter what. You have to give me 10 microamps. The VGS is less than what it is required. So what will it do? What will increase? Source is grounded. Source is grounded. You can't move that. So you look at this curve here. It's the same VGS. Let's say this current is at some VDS1. This current is at some VDS2, right? So as the drain voltage goes up, the current will increase for the same given VGS. So what will happen to this drain voltage? It'll just keep increasing till it matches that 10 microamps, right? In real circuit, what will happen is that current mirror also is a real device. So it'll squash that and it'll just kind of go close to rail. If it is greater than 0.5, then what happens? This is saying, I want more than 10 microamps. So let's say 12 microamp. The current mirror is saying, I mean, the current source here is saying, I cannot. That's my job to keep it 10 microamp. So the voltage will start going down, right? Right. So here I tweak it such that this voltage is exactly equal to 0.5. I put 0.5, then they're happy. Okay. So what can I do to create this voltage now? So you know how this is reacting. The drain voltage is reacting. Gate and drain, exactly. If I connect this gate and drain, it's a feedback now, right? Because, so let's start when the chip started. Chip started, everything was zero. VGS was equal to zero. And you started pumping this 10 microamp current, right? This gate is zero, ID is zero, right? Where will that current go? Because the current source is saying, I am going to send 10 microamp. So there is a cap here, right? Which we haven't been saying. So it will start charging that cap. So all the 10 microamp current will be flowing in this direction, right? So when this is 10 microamp, then slowly this will charge all the way to zero point 0.4. Till 0.4, this current is almost zero. So let's assume it is zero. So till 0.4 volts, this cap will just keep charging up. Once it gets to zero point 0.4 volts, there'll be some current flowing through this. Then let's say 1 microamp. So you get 1 microamp, then you get 9 here. So 9 microamp is still charging this. Then let's say you get 2 here, 8 here, 3 here, 7 here, so on, right? And then once it gets to zero cap, then this will be exactly 10 microamp and it'll just stop there. Actually, it's a feedback. So if you actually give a pulse, you'll actually might get ringing if there is a big cap or there is some routing resistance and all that, because it's a feedback. But this is a overdamp feedback. So it'll just go and settle to VGS. So if I do this, this will automatically turn to 0.5 volts. 0.5 plus. No, 0.5 is fine, right? That's what we just said. Because, sorry, because this is 0.5. What is the current here? For a 10 by 1. I just made it up. I don't know if that's true, 4.18. I'm just saying if it was true. This is 10. This is 10, right? And it just stops because the cap is charged to VGS. Obviously, the cap will start leaking a little bit, but then it'll just provide it back again. And the cap will just add the CGS. This is CGS, right? This is CGS, right? So it'll just stop there. So that's how we create the voltage. Okay. Now let's go back to the problems we talked about for the resistor and see if those problems are there. Okay. So in process, your VT is also changing, right? So like I said, zero point 0.4 volts. This could vary all the way to 0.3, all the way to 0.5 here, right? If I had the resistor one, huge current variation, right? Because the resistor is not changing that way. The VT has changed and the resistor is changing, but the VT is not changing. So huge variation. So I didn't actually point that out, but it's changing. But now if the VT changes there, I'm using the exactly same transistor very close by. So the other VT is also changing. So for example, let's say the VT is now 0.5 volts and VD sat is still zero point 0.1 volts. What is the VGS needed to create 10 microamp? 0.6, right? In the resistor case, it was still 0.5, or maybe it was lower because of the resistor. So I would have a huge error because it's 100 millivolts square times mu n C ox W over L. So it's a huge error, right? But now this will automatically make it 0.6 because that guy's VT is also 0.5 right now. VD sat is also 0.5 because the same size, they're almost close by, and then they will be fine. Okay, makes sense. So that's it. That's how you make your current mirror. So you take your current source, put it in source it into what's called a diode connected transistor. So this is called a diode connected transistors. Can you tell me why it's called diode connected transistor? Yeah, so it comes from the BJT world actually. So if you took a mirror in the BJT world, it'll be like this, right? But in BJT world, if you do this, this is nothing but just a PN junction, which is a diode. So that's why it's called a diode. So it's actually not a diode in mass, but it actually comes from the BJT world because that's how mirrors were done in BJT world, right? Same principle. It's just that now in BJT world, you have more error because you have base current. So you're stealing some base current away. So if your beta is low, you get more base current, but that's where the diode connected comes into picture. Okay, so that's it. You take a current source, plug it into a diode connected transistor that creates the voltage. You copy that into the gate voltage. Okay, but having done this, you still keep all of this together in one place and ship the current with the drain. So let's say, you have a chip. Let me just draw it here. So let's say this is your total chip, right? And your BGR is, and your current source is sitting in one side of the chip. And this is, let's say 4 or 5 millimeter by 5 millimeter, something big, right? Actually, it's not big for big SOCs, but big for typical analog eyes. Then you have one block here, one block here, another block here, another block here, another block here, and so on. So what you do is you metal route one drain to here, another to here, another to here, another to here, and so on, right? So you can do it this way, or you can take these devices, put them here, and connect the gate. Take one gate voltage, and just connect to all of them, right? What's the advantage of doing this way? Taking the current instead of taking the gate voltage? Hmm? Routing resistance? Um, routing wise, yes, you save maybe some routing, but it's not a whole lot. I square R, what is I square R? More power? No, 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 you can't use more power. You're always pumping in the same amount of current. VDS is same. It's to do with noise coupling and mismatch. Okay, because if I take, so let me show, let me just show it here itself. So if I'm taking this voltage node, so let's say this is sitting at um, the IP block 1, this is sitting at IP block 2, this is sitting at IP block 3, then this is a big route, right? This is a big route, this is a big route, this is a big route, right? And these are short ones because they're just in the same IP. Now I have some big clock signal going close by, and like I always say, everything is a capacitor in IC. They couple and they put a lot of junk noise here, right? That noise is this VGS noise here times square. The ID is going to be a huge current. So your noise is going to get coupled. You're going to have huge noise on your ID. Okay. Whereas if you have, and the mismatch part is, um, so far we have, you're saying you do W by L, you do another W by L, put it next to it, and they're same. But if they're farther away, even when they're close to each other, there is going to be a difference between their W by L. The farther they go, the difference is going to be even much larger. Okay. And if you have that, then this is also changing. And that will obviously have a direct impact on your current as well. Okay. So typically we just put all of them together. Now, so now your question is, okay, so we put all of these together in one place. So we put all of that in this band gap. That takes care of the mismatch. Now we start shipping this. So these are long routes right now. So isn't this a problem with coupling? Because now this same inverter here is going to couple to the drain side. Why is it not a problem? If I change the drain voltage of a saturation current transistor, how much does the current change by? Let's say lambda was equal to 0, ideally. How much will the current change by? Nothing. The lambda is 0.01, then it'll change by 1%. Whereas if you change the gate by 20 millivolt, it'll change by like maybe 10%, 20%, depending on what it is, right? So if you have a nice current source with a really large output impedance, right, which, when we start doing the different types of current sources, which Santanu is going to cover, you'll see that error is going to go down further lower and lower and lower. So that's why you can route a drain signal all the way, and you'll be much less immune to noise than taking a gate voltage. Okay. And same thing, if you're doing long routes and you have IR drops here, no big deal. If you're taking a gate voltage, you have a R and some current flows through it and creates a IR drop, huge difference in your bias current, right? So that's the other reason why we ship currents instead of shipping the gate voltage to all the places. Clear? Okay, any questions? Any questions? People on call? People on call are very quiet. I think they're just sleeping now.
No, sir.
No, sir. Looks like somebody is awake. All right. Uh, okay, voltage compliance, and that's something I've already talked about. Um, so now the current mirror looks like this, right? You take a current source, and that can be another current mirror, obviously. Um, but somewhere it has to be one source without a current mirror, right? And let's say we have that. So we put that into a diode connected transistor, and if this W by L, this W by L is same, and this VDS is greater than VD sat, and lambda is really, really small, let's say this is IB, then you'll get IB here, right? So whatever voltage, output voltage is here, uh, and this is simple IDS VDS curve, right? This is and so let's say if I said V out, let's say V out here. So that's your compliance region, basically. It's called a voltage compliance. In other words, so let's take an example. So let's say 0.18, this is 1.8 volts, supply is 1.8 volts, and your VD sat is, let's say, 200 millivolts. So you start becoming a current source from zero point 0.2 volts to 1.8 volts. So that's your voltage compliance. So when you provide a current mirror, you can say, okay, make sure your output is between 0.2 to 1.8 volts, then it is a current source, otherwise it's not. Okay. So that's basically, it's saying you need to be in saturation. That's what, okay. Your current source should be in saturation, otherwise the current will be not mirrored. Error in the output current due to finite out. I think I'll just kind of qualitatively mention it. I'll give you a problem, or maybe I've already given you. You can do that. Essentially, it's the same thing, right? You have, I'm just exaggerating it. Your output current is varying with VDS. So if your VDS varies by a certain amount, then your delta IDS, so let's say this is delta VDS, this is delta IDS. So that's your error in your current, right? So if this was perfectly linear, let's say, and let's say RDS was, let's say 100K, right? Output impedance was 100K. And if I say your voltage is varying from zero point 0.5 volt to zero point 0.6 volts, how much do you think the current will vary by? 1 microamp. Because 0.1 volt by 100K, right? So 100 millivolts by 100K, huh? No. 1 volt by 100K is 10 microamp. So yeah, 1 microamp, right? So that's your variation, right? So that's your error in output current. So for example, let's say you did a current mirror, right? You plugged in 10 microamp and you ship this to circuit one, and took the second one and you shipped it to circuit two. And so let's say, let's take this same example. This is sitting at 0.5. This is sitting at um, 0.6. And let's say 0.5 was giving you 10 microamps. Okay, what will be this current? It will be 11, right? If that impedance was 100K, like as you said. So that's the error in current, right? So you have to be careful. If your impedance is not high, it doesn't mean like you put any voltage across there and you'll get. So if you're sensitive to that much amount of current, then you have to fix it by increasing the output impedance. Okay. All right. Maybe this one I'll give you as a, what's the time? 3:30 as a homework. So find out the small signal impedance of a diode connected transistor. So let's say I biased it at some voltage and I'm looking at this impedance here. Okay. So everyone is kind of getting familiar what I mean by impedance, right? So it's like if I take this node, I apply some small signal voltage, V out, and it draws some current, small signal current I out, then V out by out is that impedance looking into that, right? So find this impedance. So very simple, replace this with the small signal model, right? And find out the small signal impedance, right? That's what you want to find out. This is a good one to know because in analog circuit, we'll use this impedance a lot, like diode connected transistor a lot. So good to know. But can you intuitively tell me what it will be proportional to? So if I take just a current source, for example, and I apply V out and it draws some current I out, obviously in saturation, what is this impedance? So if I just take a current source, right? And so I'm not showing the DC. So maybe let me show. So this VDS is greater than VD sat and so on. Now take a small voltage and I apply to it. I see a current going out. What's V naught by R naught? What is this? What is this? Small signal impedance looking at the output of the current mirror. What is it? GMRDS? How do you get GMRDS? I just showed you the curve, right? That's just the IDS VDS curve for it. Okay. What is this slope? RDS. So what is V naught R naught? Just RDS, right? So in your small signal, if you drew the small signal, so that is your gate GMVGS. This is your RDS. So what I'm doing is I'm applying a small signal voltage here, V out, and measuring the current, right? What will be this current? This current plus this current. What is this current? GMVGS. What is VGS? Yeah, but when I'm measuring this, there is no small signal voltage on the gate. If there's no small signal voltage in the gate, you remember how we created the small signal model, right? All independent sources, 0, DC sources. So in VGS, there should be only the DC voltage is 0, which means that's grounded, right? So that is grounded. So which means that there's no small signal gain here. This is 0, which means there's no current here. So V naught by R naught, V naught by I out is just RDS, right? So just your output impedance of this thing. Okay, but now I've taken the gate and connected to the drain. So what do you think will be the impedance, just intuitively? See, you have to, like when you're doing small signal model, just intuitively see why is it happening, right? Why are you getting RDS? Because it just, you're following this slope here, right? When you're changing the VDS, the ID will change around this slope. If it changes around the slope, it's RDS, right? So now this current here, if I apply a small V naught, what is the current which is going to draw into this? This IDS, right? And this IDS is what? G, it is the RDS plus the main current is coming from what? See, when you're changing the drain here, you're also changing what? See, you're changing, so this is a diode connected transistor. You're applying this voltage here, right? You're basically applying this voltage here. So let's say you increase this by some delta V naught, right? The drain changed by delta V naught. So I naught flowing through this because of the RDS is delta V naught by R naught, right? But you're also changing something else, gate voltage, right? But your gate voltage is huge. What is a small signal IDS current for the gate voltage delta V naught? What is this current here? Small signal, if I change the gate voltage by a tiny amount, we linearized it, right? So we don't have to write mu n Cox V VGS minus VT square anymore. I just change it by a small amount. Then the IDS is GM times VGS, right? So the majority of the current will be GM times VGS because GM is much, much larger than 1 over RDS, right? So then most of that current is going to be what? GM times VGS, right? So then the impedance looking into it will look like 1 over GM, right? Because like I said, this current mostly it's going to be the IRDS. So let me call it IRDS plus IVGS, right? IRDS is V out over R naught plus this current is GM times V naught. And I know that this current is much larger, not always. Most of the time, this current is much larger than this. So I can say, okay, this is almost zero compared to this. So V naught by I naught is what? Right? So if your GM is huge, your V naught by R naught will be, I naught will be small. So that's a small impedance now instead of a large impedance. And that's what you want, right? When you're, so this is like a TIA, you're taking a current and generating a voltage. So whatever is generating that voltage, you want a smaller impedance so that you're not changing that current too much. So it's kind of an ideal TIA kind of a terminator. So draw the small signal and see if you get an answer which is kind of 1 over GM, at least when you make all your R outs and everything infinite. Okay. So this will give you good practice of doing small signal modeling because you'll be doing a lot when you're doing AC analysis. Okay. Especially once you get to frequency response. This is no cap. So once you get to cap, then it'll add more complexity to it. Okay, I think output impedance I've already covered. So current ratios. Okay, so like as I said, um, if you have one current source and one circuit might be one, so you have a 10 microamp current. So one circuit might be wanting 10, another might be wanting 8, another might be wanting 20, another 100. So they're wanting different amounts of currents, right? So how do you provide that from the same master current? Like as I said, you can just keep copying it, and in fact, that's what you're doing it. So you say, I'm just going to create 10 of them. Whoever wants 20, I'll put two of them in parallel. I mean, I'll connect two of them because the nice thing about current is you just tie them together, they add it, right? Unlike voltage, that's the other nice thing about doing current biasing is like I can just add them and they just add together because currents add together when you tie them. So, but you just size the transistors accordingly, right? So for example, here I have taken that you're taking 80 microamps, you want, let's say 20 microamps. So you're actually scaling it down by 4x. So that means that whatever this W by L is on the left-hand side, the right-hand side should be by 4, right? Because the VGS is same, right? Because it's the same gate voltage. If the VGS is same, mu n Cox W by L, everything is same. So VGS minus VT square should change by 4x. So I mean, VGS minus VT should change by 4x. So that's why the, uh, I mean, VGS minus VT remains the same. W over L is the only thing which changes. So you change it by 4x, right? So that's what I'm showing in this current. So if your L's are same, you just change the W by whatever amount. And that's how you always want to, don't change L, okay? And that's to do with how, when you do layout, So typically in layout, so let's say this was, I'll just take a number, 100 by 1 micron. And so if this is 4x, this will be 25 by 1 micron, right? In layout, you don't go 100 and 25 by 1. Okay. So in layout, what you're going to do is typically, so in this case, I will take 20 of 5 by 1s, put them in parallel, and this one will be 5 of those 5 by 1s and put them in parallel. So that way, when you do the layout, when you do the layout, you take a single diffusion, you start interdigitizing, doing common center and all that. So that mismatch I was talking about, that delta VT mismatch, that will be minimized when you do that. Okay, so you're always going to work with unit transistors, unit resistors, unit capacitors. You're never going to do like one big cap here, one big cap here. Unless it's just a bypass cap or something, you do that. But anywhere you need matching, you're always going to do that. I'm just showing the equations. I think you guys all understand this pretty well. Problem 3.1. This is the same Johnson Martin um, second edition. So you do this. Just note down the problem 3.1. Just do it. Okay, avoiding mistakes. I think created some notes because I see a lot of times people come in and say, uh, something like, oh, what's the output impedance? And they'll say like 100 meg or 2 ohms or 5 ohms, something like that. And that's usually because they mess up the units and they remove like 10 to the power 6 somewhere, 10 to the power 3 somewhere and do it. So, you know, different people have different ways to kind of minimize that mistake. And what I do is, for me, I keep similar units. So for example, if I'm working in length is in micrometer, then you keep the lambda as micrometer per volt too, right? And ID as 20 microamps. So then that way the units all kind of nicely cancel, because otherwise if I keep lambda in meters and this, then I'm just always carrying the 10 to the power minus 6, and that's where you get into errors. Same thing, if you're doing kilo ohms and this thing, instead of doing 0.2 milliamps, 0.02 milliamps, carry them in microamps, because then like 10 microamps times 10K is 20 millivolts or 10 millivolts or whatever it is. Okay. So carry the units in a such a way that they're easy to kind of calculate. So same thing, I say here, when you're uh, calculating V effective, for example, so typically your mu n Cox is given as microamp per volt square, right? So then keep the ID in microamp, right? Then that way you don't have to carry the 10 to the power 6s and minus 6s anywhere. You just go 20 over 92 and you're done. Same thing, W over L, um, L over W, I mean, that's obviously you keep it in micron. Okay, so here I'm just showing a small example of mismatch effect. So you can see if your VTN mismatches by 5 millivolts, uh, because this, so let's say this VT was 0.4 volts, this will be 0.405, right? Volts by extra amount. Might seem very small, but this is actually varying the gate voltage, right? So the effects are always huge when they're doing gate. So if you do that, you'll see that what is the unit current? Okay, yeah. So instead of 20 microamp, you're getting 21.26, which is, sorry, 1.26. So what is it? 1% is 2. So no, 10% is 2, right? So close to 10%. I mean, 5%. 5% is a huge error. I mean, depends. Like if you're doing a DAC, for example, and current DAC, and you're trying to do 10 bit, then obviously you're dead, right? This is not even close, depending on what it is. So depends on your circuit. So that's why the mismatch is very important. And how do you um, negate the mismatch? So these are foundry parameters. So they will give you some mismatch where it's delta VT over the square root of the area of the transistor. So you have to calculate that before. If you can't tolerate it, you just have to keep increasing the area of the transistors. There's no other way. I mean, there are ways, but then your architecture becomes complex. So you start doing chopping and all that stuff. If you want to do brute force, you just keep increasing the area of it. Okay. So that's all I want to cover with simple current mirrors. So I think hopefully that's given you how to do small signal, what's the motivation behind doing current mirrors, serves both as your bias as well as your active load for your amplifiers or source followers or whatever you're doing. Um, and then how did we create a simple current mirror? And then now the complex current mirrors like the cascodes, the wide swing cascodes are just building on top of this, basically. Same principle, we're just trying to improve them, basically. Okay, and I think maybe next class, maybe Santanu, you can, take some of the cascode and full swing cascode ones. Okay, any questions?